Hi guys, and welcome to 8.3. This is hyperbolas, so it's the last conic section. We've already done parabolas and then circles and ellipses, and then today is hyperbolas. 8.4 and 8.5 talk about how you could potentially combine conic sections with vectors and matrices to rotate a conic section and have it open up at a certain angle instead of vertically or horizontally specifically. But we won't be covering those. And then 8.6 is graphing in the three-dimensional plane, which sometimes we cover, but we're not going to cover this year. So this is the last section that we'll be looking at in chapter 8. So a hyperbola's definition is very similar to an ellipse's definition in the fact that it's the set of all points in a plane whose distances from two fixed points in the plane. But now instead of having a constant sum, so that you would add those up and be the same, which is the definition of an ellipse, a hyperbola is that those distances have a constant difference. So 9 minus 2 is 7, 10 minus 3 is 7, etc., right? So that whatever the lengths are, that their distance or their difference when you subtract them would be constant. So that one is a little bit harder to construct as far as like with a string construction. So I'm not going to point you to one of those. And we're just going to move right on to the anatomy of a hyperbola. So I've gone ahead and started drawing it a little bit to help us out with guys having to wait on me while I draw. So just like the others, that they all have some sort of center, right? So here's the center. And what we would normally call the major axis has a new name now for a hyperbola. It's called the transverse axis now. The transverse axis. You can think of it as the major axis, but there you go. It's called the transverse axis. And instead of the minor axis, that has a new name as well, and it's called the conjugate axis. And another one of the differences between the hyperbola and the ellipse is that for a hyperbola, turns out that we're going to go ahead and we're going to take the vertices and we're going to take the minor axis or conjugate axis endpoints. And the way that we're going to construct this hyperbola is that we're going to draw a rectangle formed by the vertices and the conjugate axis endpoints, which would be the A and the B, just like in ellipses. We're going to make that rectangle, and then we're going to draw diagonals through that rectangle, like so. And turns out then that where the hyperbola lives is that the hyperbola lives so that it hits each vertex, but the diagonals that I just drew in, turns out that those are going to be asymptotes for each part of the hyperbola. So a lot of people think that hyperbolas are a parabola on top of each other. That is not true, because a parabola keeps getting steeper and steeper as it gets farther away from the vertex. A hyperbola does not keep getting steeper and steeper. In fact, it approaches the slant of whatever this diagonal is. So it gets close, 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 and then it sweeps out, hits the vertex, and then gets closer on the other side as well. Same thing here, it would be start at close, and then hit the vertex, and then swing out and get arbitrarily close to the diagonals. And I've kind of put the hyperbola at a tilt for you because we will be doing vertically oriented as well as horizontally oriented hyperbolas, and I didn't want you to get locked in your head that it had to be one way or the other. So turns out then that the focus points of the hyperbola are actually farther away from the center than the vertices are, because a hyperbola is focusing outward and not inward like the ellipse, right? The ellipse, it makes sense that the foci were on the inside because the ellipse was focusing inward, but the hyperbola, because it's focusing outward, that's why the focus points are on the outside. So that would be the anatomy of the ellipse. Also, we want to go ahead and be able to label our A, B, and C. So the distance from the center to the vertex is still A. And the distance from the center to the minor axis or conjugate axis endpoint is still B. And the distance from the center to the focus, let's pick a different color, distance from the center to the focus is still C. But now the difference is that which one is biggest, A, B, or C? Turns out C is bigger. And so the Pythagorean identity, a squared plus b squared equals c squared, is the one that holds true for hyperbolas. So c is the biggest length there, and not a like it is in ellipses. However, in ellipses, A has to be bigger than B because A was the biggest, right? A was the largest side, or the hypotenuse, if you would move it around. But in this one, because A and B are not the biggest sides, turns out that A does not have to be bigger than B. A can be less than B. It doesn't really matter. So let's just go ahead and do a couple of examples. I also want to give you the template for the equations. So here we are. These would be the equation templates for hyperbolas. Notice that there are a couple of differences between this and ellipses. So it's almost the same as the ellipse template, except that this would be a minus sign, right, or a subtraction sign instead of adding those two terms. And then also with an ellipse, it didn't matter whether you put the x first or the y term first because we were adding them up anyways. But with a hyperbola, it turns out it does matter, because subtraction is not commutative. So if the x term is first, then that means that it opens horizontally because the x term is first, and it would look something like that. But if the y term is first, then that would mean that it's a vertically oriented hyperbola, and it would open up down. If it opens sideways, then the distance from the center to the vertex here, that's A, and that's in the x direction, so it's underneath the x term. But if it's vertically oriented, then the A, which is the distance from the center to the vertex, is now in the y direction, which is why it has to be underneath the y quantity. And so they don't get to always be with one or the other, and so you have to pay attention to that a little bit. Let's do a couple examples. So here we go. Find the hyperbola whose transverse axis has endpoints -2, 3, and 6, 3, whose conjugate axis has length 6. So go ahead and pause the video and see how much you can get done without me, and we'll start again in 3, 2, 1. All right, so if we had just looked at the information that's given to us, notice that -2, 3, and 6, 3, those are my vertices. So they're the endpoints of the transverse axis, and so those are the vertices. If I wanted the foci, then that would be the endpoints of what we would call the focus or focal axis, which is the same as the transverse axis, but just a different length. So there's -2, 3, and here's 6, 3, and I would go ahead and label those as vertices so I don't confuse myself for later. And then that also means that I know that the hyperbola is going to be oriented horizontally, which means that I know that the x component is first and then the y component. So I'm going to go ahead and set up a template here so that I remember that the x component is first. Then let's go ahead and find the center. So we would find the center by just splitting the distance between our vertices. From -2 to 6 is 8 units, and half of 8 is 4. So if I go 4 units each way, I can get that the center is at the coordinate 2, 3, the set of coordinates 2, 3. And then if the conjugate axis has length 6, then I know that that's 3 units each way. So I can move up 3 and get to one endpoint, and I can move down 3 from the center to get to the other endpoint of the conjugate axis. The conjugate axis doesn't show up in the picture other than it creates, if we go ahead and draw the rectangle, it creates the size of the rectangle, which tells us how steep or shallow that the hyperbola is going to open. So there's the rectangle, and then I can go ahead and draw my dotted lines through. Please forgive the sloppy nature of my graph. So I can actually draw the hyperbola in without having the focus points on there. I can go ahead and draw the hyperbola if I wanted. I know it's gonna sweep through, hit the vertex, and approach the other asymptotes. Same thing here, sweep through, hit the vertex, and approach the other asymptote. Try to make it as smooth as possible. Like here, I went farther away from the asymptote after I was already closer, so please try and be careful about how you would sketch that. But that would be what the hyperbola would look like. And then I can also go ahead and fill in the rest and fill in the equation. So knowing that the center is at 2, 2, and that's 4 units away from each vertex, that means that I know that A is 4. And so I know that the Pythagorean identity for hyperbolas is a squared plus b squared equals c squared, which means that c in this case must be 5, which means that the focus points must be 5 units away from the center. So I would have 1 at the point 7, 3, and 1 at the point -3, 3. Those would be my 2 focus points, and so I could go ahead and label them as focus points. Technically, you should put 1 and 2 because we shouldn't have 2 points that are labeled with the same letter on the same graph, but it doesn't really matter to me. You can just label, you could label them both with just capital F's or capital V's, and then that's fine. So the only thing left that we would have to do is the equation. The center is 2, 3, so x minus 2 and y minus 3. The distance I'm going out in the x direction, or the a value, is 4, so 16 is my first denominator. And the transverse, semi-transverse axis was 3, and so 3 squared is 9, and that's what would go underneath the y term. And then we could check this if we wanted by graphing this on the computer. We could type that into Desmos or something and make sure that it looks correct. Here's another one. So I would like you to take that equation and fill in everything that you can, and I'll do the same. And we'll meet back up in 3, 2, 1. All right, here you go. The only thing I haven't done is put the focus points on there, and that's because I wanted to talk to you about that. So please check your work. See how you did. So, and then we can talk through how we got each part of that. And I'll go ahead and label. There you go. So I took the center from the equation, -2, 5, and then the x distance was 3, and I knew that that had to be a because that one was first. So because the x term was first, that's how I knew it opened horizontally. So a was 3. I knew that because the 49 was underneath the second term, that made b 7. And then doing the Pythagorean Theorem, 9 plus 49 would be 58, so C is root 58. I did not put this in a calculator. I just said if root 49 is 7 and root 64 is 8, then root 58 would be 7.5, 7.6, 7 point whatever, right? But somewhere in between 7 and 8 is the important thing, because without a calculator, you should be able to place that on the graph. And so on the graph, it doesn't actually matter if it's 7.5 or 7.6 because I can't tell anyways. So I just ballparked it, 7.5 is fine, or 7.6. So then I'll go ahead and put everything on the graph. Notice that part of it went a little bit off the graph. That's fine, just estimate what 7 units would be there to go up. And then I drew my rectangle and then put the diagonals through so that I would know the asymptotes of the graph. Notice that because this one is wider, right, or more shallow for each one, the foci end up being farther from the vertices than they were in the last one. So hopefully you had this right. If not, check your work and correct it and see what you would need to do to fix that. Here's our final question, and we may not do all of this, the vertices and the foci and the eccentricity, but I at least want to make sure that you are aware how to how to deal with the completing the square, and we're going to complete the square twice here, right? Because we have to get this in a standard form for a hyperbola. So we're going to start by collecting the 25y squared minus 50y. And then let's collect the negative 9x squared minus 54x. And the 281, I'm going to move to the other side because I don't care about it. We're going to make that 1 anyways here in a little bit. So then the next step would be to factor out the 25 from the first terms, the y terms, and to complete the square with what remains. So half of negative 2 is negative 1. And negative 1 squared is positive 1. And by putting a positive 1 there, then what I actually have done is I've actually added 25 to the left-hand side because of the distributive property. So I'll add 25 to the right-hand side as well. In class, sometimes we had done it as adding and subtracting from the same side, but because these are on 2 different sides, I have to add to each side, right? I'm going to do the same thing with the x's. I'm going to factor out the negative 9 and get x squared minus 6x and then leave that blank. Half of 6 is 3, so this becomes x minus 3 quantity squared, and 3 squared is 9. But by putting that positive 9 there, turns out what I've actually done is subtracted 81 because of the negative 9 that was on the outside. And so if I subtract 81 on the left, I need to subtract 81 on the right. So then if I go ahead and figure out what this right-hand side is, 281 minus 81 plus 25 would be 225. And then to get this in standard form, I would need to go ahead and divide each term by 225. So 225 over 225 would be 1/9. So I get y minus 1 quantity squared over 9 minus, and then 225 into 9 becomes 1/25. So I get x minus 3 quantity squared over 25 equals 1. And that would be the equation, and that proves that this is a hyperbola because I've written it in standard conic form for a hyperbola. And then looking at this, we can look at a couple things. First off, the 25 and 9, they ended up switching and becoming the 25 and 9. Does that happen every time? No, it doesn't. Sometimes it does, but not all the time. So please don't just bank on that like, oh, look, they're always going to switch. No, they don't. Sometimes, but not always. And then let's go ahead and look at some of this other information that we were asked to find. The center here would be 3, 1. So the x coordinate always comes first, even if it's the second term. And the a distance, if 9 is my first denominator, that would mean that a is 3, but that's in the y direction. So I need to go 3 up and 3 down to get to the vertices, which means that the vertices are going to be 3, 4 by moving 3 up, and 3, negative 2 by moving 3 down from the center. The b value would be 5, which I'm pulling from the second denominator here. And so then if I do the Pythagorean theorem, I get c would equal the square root of 34, which is the 25 plus 9. And so I know that my foci have to be on the same axis as the vertices are. So from 3, 1, I'm simply moving up and then down root 34. So I would get 1 plus root 34 for the 1y coordinate, and then I'd get 1 minus root 34 for the other y coordinate. And root 34 I need to know is approximately what, 5.9 or something. Root 36 is 6. So when I would put it on the graph, I would know where exactly to put that on the graph. So the question asked that I find the vertices and the foci, which I did, and I could graph it if I wanted to. And it's also asking for eccentricity. Eccentricity, just like with the ellipses, eccentricity is still c over a, but because the focus points are farther away from the vertices, that means c is bigger than a, which means that this is top heavy. So c is always going to equal something greater than 1 in a hyperbola, because hyperbolas are eccentric. And so in this case, c is root 34, and a is 3. And so the eccentricity of this hyperbola would be root 34 thirds. Root 34 over 3. Sorry, let me be more specific. And I believe that that's all I have for you. So good luck on your hyperbola homework. And let me know if you have any questions. We'll have office hours for this so that you can ask if you have issues. Good luck. Bye.